Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to go over amides. And now we're at the very bottom of our list here of the class 2 reactions or class 2 molecules. So this is a very quick and short video. All we can do, if we go back to our chart, so here's our master chart, and remember, all we can do at this point is we're at the amide. We could only make it become carboxylic acid. That's the only thing we could do. Remember, this works top down. So this is the most reactive. It can become everyone below it. This can only become what's below it. So as you work down this list, you get to the point where you're at the amide. And amides, there's nothing below it, so it could only become carboxylic acid. Remember, carboxylic acid, every molecule can become it, no matter where it is on this chart, and it can become every molecule. So that's what makes it so special. It's that gateway molecule. It's the one that you could turn anyone into or become anyone from. Okay? So that's the story here. We're at the amide. We only have to learn this one reaction, but I'm also going to add nitrile. How do you make a nitrile out of an amide? We'll add that into this section as well. All right, but that's it. And after this, it's just all about problem solving for the rest of the chapter. All right, so let's get started. Let's talk about the first thing, A, is how do we go through hydrolysis, or let's say number one, hydrolysis with amides, or amide hydrolysis is another way to write it, but hydrolysis with amides. So A, there's the acid pathway, and so in the acid pathway we have a amide, and we want to turn it into a carboxylic acid, right? So this plus water, and it's going to be an acid. So what's the mechanism for this one is really the same as everyone else, but I'll do it real quick. Protonate the oxygen, right? That is the most basic, and we know why. Even though nitrogen is more basic than oxygen, this nitrogen is not. In this, for the carbonyl oxygen, because this has resonance, this goes up and becomes negative, right? And so negative is more basic than neutral. And when that nitrogen does resonance, it becomes positive, right? So it's not basic. It's not like other nitrogen types. So that nitrogen here is not considered basic. And so we're going to protonate the oxygen. We're going to make it positive. And now what's going to happen is water is going to come in, right? Water comes in. This opens up. And as always, because oxygen and nitrogen are very close on the periodic table, we have to do a proton exchange, right? We want to make sure that the nitrogen is the leaving group. Right now, it wouldn't be. If this closes back down, the O is going to leave because whatever's positive is going to leave, right? So we're going to do a proton exchange. We're going to swap a proton over to the other side. And now we have the nitrogen ready to leave. So it looks like that. And from this point, this closes down, and we kick out the nitrogen. And so we get to this point here, OH, positive, plus NH3. Now, nitrogen is, right, this is an amine, and it definitely is a base, right? So this is now a base. It's not like an amide nitrogen. So from here, we would just pull that H and get to the carboxylic acid plus NH4. And there you have it. So that would be the end of this reaction. Usually we have some sort of counter ion balancing this. So we might have like some metal. Sorry, not metal. So we'd have some other base around that would balance that nitrogen out. But that's it right now as it stands. So what we did is we protonated the carbonyl oxygen. We went through this process. We brought in water. We know water positive is going to leave, so we swap the proton over, and then we close it back down. Very straightforward, right? Especially after all the other work that we did together for this chapter. Now, this next one, B, is actually a little bit different than what we've ever seen. So here's the base version of this reaction, okay? And this is different. You have to see this, because if you didn't see it with me now, you wouldn't think this is what happens on a test. So let's go over it right now. So when this comes in and this opens up, right? Because remember, this we know. Base hydroxide comes in, or whatever the base is comes in. Now, here's the issue. The issue is that normally when something comes in, when this O closes down, it's going to throw out the one that's already there, right? We could do Le Chatelier's principle. Le Chatelier's principle is not going to work unless we modify this even further. So in order to get this to close down and to throw the nitrogen out, you can't expect it to happen now. And the reason why is because oxygen is a better leaving group than nitrogen. Okay, oxygen negative is more stable than nitrogen negative, right? Oxygen is a weaker conjugate base, right? OH minus is a weaker base than N minus, right? So right now, it's not going to leave. So it turns out that you actually have to have an extra hydroxide around, an extra equivalent. So it could be where they write this is an excess, but you need extra hydroxide to deprotonate that OH. So you have to make it really basic. And you need to get 2 negatives in this molecule, something that you're not used to seeing. Okay? But you have to do this because now when you think about an O leaving that's negative, it becomes -2. That's not stable at all, right? So the oxygen now is not the good leaving group. Nitrogen is. You'd rather have something leave as a -1 than leave as a -2. The less negative, the more stable, right? So that's why we had to do this. So you had to recognize that there's a very strange looking intermediate. Something that we normally choose not to do is to show more than one charge in our intermediate molecule, right? But we're going to do that here. We're going to shut it down and throw out the nitrogen. So now we have a carbonyl, a carboxylate plus NH2. And then from here you can have water or something protonate that NH2 because it's negative, right? So you could have something protonate it. And then it becomes COO minus plus NH3. And that's the product right here. Okay? So realize that you, as you would expect, by the way, if you're in a base environment, right, you make a base version of carboxylic acid, right? That we know. We've seen that several times over and over throughout this chapter. Okay? But what's really unique is this intermediate. Remember this, because if they give you a multiple choice question and they say which is not an intermediate, you might see this 2 negatives here and say that's not an intermediate. And really, under most conditions, it wouldn't be, but here's an exception. Okay? So when you take an amide to turn it into a carboxylate in base environment, you have to make a -2. A negative twice on the oxygen. 2 oxygens that are negative, sorry. Okay? So they have it. So that covers this right here. So you have the acid pathway, you have the base pathway. Remember another thing, that a nitrogen on an amide is not basic. It's not like an amine, right? Because the nitrogen on an amide is definitely not basic compared to the double bond O. The double bond O is more basic because it becomes negative through resonance. Okay? So this is more basic than that, and now you've got that stuff down. Now the next thing I want to talk about is I guess how to turn, let's call this number 2, an amide into a nitrile. So this is something that comes up now really because there's not much to say about amides, so they kind of throw a little bit more extra details in there. But you know, basically that's what's happening. But what happens is if you have, let's say, an amide and you want to convert it into a nitrile, one way to do that is to actually go like this. You can use an acid anhydride and treat it with an amide. And what's going to happen is this right here is going to wind up doing resonance, like I had mentioned to you, because the carbonyl oxygen can become negative, and that's what we need to have happen. We need the oxygen to be negative so that it can go after one of these carbonyls. Okay? And so you wind up getting a connection like this while this opens up. So you wind up getting a double bond NH2 plus, and now you have an O that's connected to an O minus, and like that, right? The acid anhydride. All right. So this is the first thing that happens. Now, the reason why this happens is because you want to turn the oxygen here, this oxygen above now, into a leaving group. That's ultimately what we're trying to do. Okay? So the next thing that's going to happen is this is going to close down, and we're just going to throw out that as a carboxylate. So there, we're just going to stabilize it. So now you have this right here, NH2, but you have an O that has a carbonyl attached to it like that. Okay, and so that's the next part. Now, like I said, that plus this right here.